The easiest way to demonstrate recursion is with an example. But since we're staying away from actually showing the implementation of these algorithms in this course, we'll keep it in terms of natural language. You can implement them in the language of your choice. Now, first, if you aren't familiar with it, let's define the factorial operator. It's a mathematical operator that you might have covered a bit in your previous math classes, but if you haven't, don't worry. The factorial of a number is specified by an exclamation point following the number, and it's equal to the product of that number times every previous number down until 1. So 4 factorial is equal to 4 times 3 times 2 times 1. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. 20 factorial would be equal to 20 times 19 times 18 times 17, and so on until you get to 1. You get the picture. Now, what makes factorial a good candidate for demonstrating recursion is that itself can be thought of as a recursively defined function. The factorial of any given number equals itself times the previous number factorial. 4 factorial was defined as 4 times 3 times 2 times 1, and part of 5 factorial was 4 times 3 times 2 times 1. So we could take 4 factorial and put it in for that portion of the function, and we would get 5 times 4 factorial. The same way, we could define 4 factorial as 4 times 3 factorial, 3 factorial as 3 times 2 factorial, 2 factorial as 2 times 1 factorial, and 1 factorial we would just define as 1. So written this way, if we want to look up 5 factorial, we need to look up 4 factorial, which necessitates looking up 3 factorial, which necessitates looking up 2 factorial, which means we have to look up 1 factorial. And finally, when we look up 1 factorial, we find the value 1. So 1 replaces 1 in 1 factorial, and we get 2 times 1, which is 2. So 2 replaces 2 in 2 factorial. 3 times 2 is 6. So 6 replaces 3 factorial in 4 times 3 factorial, which is 24. And so 24 replaces 4 factorial in 5 times 4 factorial. And so our answer is 120. The way I've drawn these arrows is useful. Every time, we drew an arrow that jumped down a level until we reached the bottom. And then when we reached the bottom, we drew a bunch of arrows that took us back to the top. That's how a recursive function works. It keeps calling another version of itself until it reaches some default condition. In this case, the default condition was that if I call factorial on 1, just go ahead and return 1. But if I call it on any other number, return that number times 1 fewer factorial. And you might also notice how this is a little bit related to our idea of a stack. We kept adding new functions on top of the stack until we reached the bottom, and then we removed them in the opposite order from how we added them. This is a perfect example of a recursive function. And here it is in pseudocode. Pseudocode means a loosely code-like format that might not be exact, but kind of gives you a picture of the way the logic works. The factorial of a number is calculated by first checking to see if the number we've passed in is greater than 1. If it is, then we return that number times the same function, factorial, with n minus 1. This is called a recursive function because part of the body of the function includes the function call itself. So the function factorial will actually also call the function factorial. But it changes the argument, which is what prevents this from just looping infinitely. Each time it runs, it gets 1 closer to reaching that bottom out condition. So if I run factorial of 5, I'll just abbreviate it with fac, then 5 is greater than 1, so it's going to call factorial of n minus 1. N was 5, so it's going to call factorial 4. Factorial 4 is still greater than 1, so it'll call factorial of 3. That's still greater than 1, so it'll call factorial of 2. That's still greater than 1, so it'll call factorial of 1. Each of these will be multiplied by the previous number. So 2 times factorial 1, 3 times factorial 2, 4 times factorial 3, 5 times factorial 4, and those results will give us factorial of 5. Factorial of 1 is going to become 1, which means that 2 times factorial 1 will be 2. So we replace factorial 2 with the number 2, and 3 times 2 is 6. So we'll replace factorial 3 with 6. 4 times 6 is 24. So we'll replace factorial 4 with 24. 5 times 24 is 120, and so our answer is 120. Again, notice how we went all the way down, and then all the way back up. And notice how going down was terminated by that null condition. It was because we knew to eventually just return a number instead of a function call that we were eventually able to escape this recursive function call. This is why we noted that the stack was more common than the queue in computing. It's very common for function calls to work like this, where calls are added to the top until one is ready to return something. In this case, I visualized it as the bottom, but the important thing is that the first one to return was the last one to be called.